All right, so that was quiz 3. We'll grade it and we'll carry on. Looks like a bunch of students disappeared. I guess that's okay.
Can we get the coin?
What's that?
I guess it's a...
I'll wait till the end of the class.
Yay!
I could use Arabic.
Okay. Let's see.
Me too,
So
to
we
get
just
an
have a few more weeks, okay? We've got this week, next week, in terms of covering new content, and then in 2 weeks we'll have a final exam review, and then the week after that the final exam. Okay? So not a ton of stuff. Or actually, I guess 3 more weeks of content, and then the final exam review, and then the final exam. You have a quiz in 2 weeks, and after that quiz, I will recalculate everyone's grades and let you know exactly how you must perform on the final exam to get the grade you want. Yes.
And can you do it before that, so to see how well we are doing currently in the class without just making, you might have to use like quiz 4 as well.
I think it's worked the way it has been. I'm not going to trouble myself with generating a whole nother set of emails. It's actually a bit of work. So I think I'm nice enough with the amount of emails I'm sending out to let you know. Okay. All right. Just flipping through and looking around. I think maybe some people struggled with this last chapter, which is unfortunate because today's stuff builds off of the previous week's stuff. Okay, so everything builds up. So you guys have to stay up to date. Okay. Today we are going to cover chapter 7. Sorry, chapter 8. Chapter 8. My bad. You guys are keeping me in check here. Okay, yes. Last week we did chapter 7. This week we're doing chapter 8. All right, and we are continuing inference for proportions. Okay, so this is more inference for proportions. And specifically, we will learn hypothesis testing. Okay. Hypothesis testing for one sample, proportions, and hypothesis testing for 2 samples. Okay, again, proportions. Last week you guys learned an inference method. What was that called? What's that? That's not an inference method. That's the theorem upon which the inference is built upon, but the practical application was confidence interval. Okay. Okay, this was last week. Okay, but these are the 2 things we are learning today. Again, the idea behind inference is that we want to understand the population. The population is not directly observable. So we observe a sample, and from the sample, we try to understand something about the population. Try to learn something about the population. Okay, and so just to put things in perspective, what you guys learned last week, okay, was confidence intervals, alright? And you had a sample, let's say n equals 200 or something, okay? And maybe you flipped a coin 200 times and you got heads 100 times. Alright? Let's say you don't understand anything about coin flips, okay? So based on your sample proportion is 100 over 200 or 0.5, exactly. You create a confidence interval, which is p hat plus or minus some z star times the standard error, and maybe it's going to be 0.5 plus or minus, and I'm completely making up numbers here. Let's say it's 0.04. Okay. So your confidence interval is 0.46 to 0.54. So with a confidence interval, you've observed a sample, and you've created this confidence interval, and this says something about what? It says something about P, the population proportion, okay? This okay, and what does P represent in this scenario when we're talking about coin flips? It represents what? It's a parameter. What is this parameter?
The head of coin flips out the heads out of the population.
It's the
percentage of heads.
okay. All right, you guys are just saying stuff. Okay. P represents the proportion that a coin lands heads. Or I'll say P is the proportion that a coin lands heads in the population. It is not heads, the number of heads, it's the proportion.
That lands heads in the population?
Lands heads, yeah.
That's
Sorry.
what I said.
Is that what you said?
Yeah.
Okay. Alright, I didn't hear it. Everybody, other people were saying things that were not quite correct. Okay. So, that is our confidence interval. And so we observed a sample. From the sample, we create a range of plausible values for P. That's one inference method that you guys learned last week. Alright, this week, the inference method we are learning is hypothesis tests. And over here, we are going to observe, well, first we're going to create a hypothesis. Okay, we're going to create a statement about the population. Okay. A statement about the population. And in our case, it's going to be a statement about the population parameter P. Okay. In a hypothesis test, we first create a statement about the population, and then we observe our data. We observe a sample or observe our data. And then we ask the question, does our data contradict this hypothesis? Or does our data contradict the statement we made about the population? So this is kind of the framework that we work with for hypothesis tests. This is different from confidence intervals. Confidence intervals, we didn't have any kind of statement about the population. We just observed data and we said, what does this data say about the population? Okay, and we made a confidence interval. Over here, we first make a statement about the population, we observe data, and then we ask, does our data contradict that original statement? Right. Is that okay? Now, how can we check this thing? Does our data contradict the statement we made about the population? Let's just hypothetically think of an example. Okay. So let's say we're talking about coin flips, and someone's going to make a statement about the population. The statement they make about the population is that they say, a coin lands on heads with probability 0.5. Okay, so let's just try a So first someone makes a statement. Alright, in this case this is our hypothesis. And they say something like, a coin lands heads with probability equal to 0.5. That sounds reasonable enough. Okay. And someone says, well, let's see if this makes sense. So we go out and we flip a coin. Let's say we flip a coin 100 times. So we observe some data. New data coin. Okay. We flip a coin 100 times. Alright. How many times will this coin land heads? 50%. It might. Could it land 52%? 52 heads? Okay, let's say we go out, we flip a coin 100 times, and let's say it lands heads 53 times. Is that okay? Seems reasonable. Okay, so my sample proportion p hat is equal to 0.53. So, does our data contradict the statement we made about the population. My data,
Yes.
my data says my sample proportion is 0.53. The statement I made about the population is that a coin lands heads with probability 0.5.
Not really, because it's so close.
Okay, so yeah, so my question is, does our data contradict the statement?
No.
So you say,
No.
not really, what?
Because the numbers are so close.
So you're saying 0.53 is close to 0.5, so it doesn't contradict. Okay, yeah. What, you think it does? Okay. So we got some opinions here. Okay. Who thinks this contradicts the statement of 0.5? Anybody? Okay, we have maybe about 5 people. Okay. And who thinks it doesn't contradict? Okay, maybe like 9 people. Okay. So we have 14 people participating. Okay. What if instead of it landing 53 times, what if it landed heads 58 times? Does that contradict? So some people say yeah. Huh? 58? Huh?
Yeah, I contradict.
At 58 times you say it contradicts.
Yeah.
Six, at 62 times does it contradict? So you guys are saying at 62 it contradicts, 53 maybe not. What are you saying?
Like
Give or take 5%. Where did you come up with that number?
on the news it says like this is the amount of people who like support whoever, and then give or take 5%. So like maybe there's like a 10% range up and down.
Okay. You know, sometimes the news is trustworthy, sometimes it's not. Sometimes we could learn things from it and apply it to that, but this is not one of those cases. So that 5% rule, it may or may not apply. Okay. All right. So at 0.53, maybe we will say doesn't contradict. Okay. But then if the sample said sample proportion p hat was let's say 6.2, we'll say probably like contradicts. And then so where do we draw the line? How do we decide if my data contradicts this original statement? Huh? Okay, all right. So these are the questions that we should be thinking about. How can we draw a line that says this is when we're going to say it contradicts, and this is when we're going to say it doesn't contradict? Okay, think about that.
Where did you get the 62 from?
Contradicts the hypothesis.
Why is there a question mark next to contradict?
Contradicts, does it? Okay, we'll just say contradicts. Well, I'm saying it might. It might. Maybe it's not necessarily. It may or may not necessarily at this point. But you guys have a suspicion that it contradicts the data. Is that okay?
Yeah.
All right. Is everybody with me? This
No.
idea here. Okay. So this is what I propose as to how we can decide whether or not the data contradicts our hypothesis test, or our hypothesis. Okay, so the original hypothesis Alright, so we'll just imagine this, right? I've got a coin, I say this is a fair coin. So that means if I flip it 100 times, it should land heads about 50 times. Maybe it lands heads a few more than 50, maybe it lands heads a few less times than 50, right? That's what we've got. I've got a coin. Now let's say I actually go through and I flip the coin 100 times. And it lands heads 62 times. Alright, so what are you guys thinking now?
The sample size is
That's not what you would be thinking, okay?
There's something wrong with the coin.
What?
There's something wrong with the coin.
Yeah, you might say, okay, well, it landed 62 times. Is that, you'd say, maybe there's something wrong with your coin. Maybe the coin the coin seems to be landing heads too much. Okay, maybe we'll think that, okay? Or if I flip a coin 100 times, and let's say it lands heads 80 times. Okay, what will you guys think?
Something's programmed.
Something's wrong with your coin. You're cheating, you're doing something. Let's say we played a game, right? I say, okay, I'm gonna flip a coin 100 times, and if it lands heads less than 50 times, I'll give everybody an A, okay? But then we flip the coin and it lands heads 80 times. So I say, oh, nobody gets an A. What was that? Yeah, you'd say, all right, probably your coin is cheating, right? You're doing something, you're not playing the game fair, right? Something like that. You might be thinking that. Okay. So this is what I'm saying. Okay, so this is our hypothesis. Our original hypothesis is that the coin lands heads 50% of the time, okay? With probability equal to 0.5, okay? Or, if I just wanted to do this symbolically, I would write P, where P represents the proportion it lands heads. I'm going to just write P is equal to 0.5. So this is what we call the null hypothesis. Or we call this H0. H0 is that P is equal to 0.5. The alternative is that
H0 is the null hypothesis?
Yeah, H0 is the null hypothesis.
Do we always write H0?
Yeah, we always write H0. Okay? Okay? And the alternative is that my coin is cheating somehow. Okay? We don't care how, we're just saying that it is. Okay, and so the alternative is that P doesn't equal 0.5. Or P is greater than 0.5 or something, okay? Alright, so I could say this is how we decide if our data contradicts our null hypothesis or not. Okay, I could say just for argument's sake, let's say my coin landed heads 62 times, and you say, I think your coin is cheating somehow. I don't know what's going on, but 62, that seems like it landed heads too many times. Something doesn't seem quite right. Okay, so at this point, you have two options. You can either believe the coin is fair and that I just happen to get really lucky and get 62 heads, or maybe the coin is cheating somehow. Okay? So we could say, if we were to assume that the coin is fair, just for argument's sake, let's assume that the coin is fair. What's the probability that it would land heads 62 times? Does that question make sense? Okay, so if we assume the coin is fair, what is the probability that it lands heads 62 times, or more, really? Because if the coin lands heads 62 times, then that raises your suspicion about whether the coin is fair or not. It would also raise your suspicion if it landed heads 63 times or 64 times or anything more than 62 times, right? If it raises your suspicion at 62 times, it'll certainly raise your suspicion at anything higher than 62. So that's why I'm saying 62 times or more. Okay. Alright, can we answer this question? If we assume the coin is fair, what is the probability that it lands heads 62 times or more? Can we answer this? Yeah? No? Yes? Okay, how do we answer this? Yeah, okay. Alright, so if I say go ahead and find the answer to this question, can you guys do that right now?
Yeah.
Okay, go ahead and try. And if you're totally stuck, I will start dropping hints along the way, okay?
Do we do z-score?
Yeah, there will be a z-score in here.
Is it still flip it 100 times?
So p is equal to 0.5. Alright, I'll just work through this, okay?
Yeah.
Alright, so what happened is, we're assuming that p is equal to 0.5.
Mean is 5.5.
Yeah, my mean is 0.5, okay? So whenever I flip a coin 100 times and I calculate the sample proportion, p hat should have what kind of distribution? So n is equal to 100. P hat comes from what? A normal distribution where the mean is equal to 0.5 and the standard deviation is what? 0.5 times 1 minus 0.5 over 100. Yeah? Okay. Anybody lost already? Yeah.
Wouldn't it be the standard error instead?
We're talking about the standard deviation of the sampling distribution, so it's still the standard deviation. Okay. If we were making a confidence interval, it would be the standard error, but the standard deviation of the sampling distribution. The concept is analogous to standard error. Yes. I said 62
That's
times or more. I guess
0.05.
I said I flipped the coin 100 times somewhere in there.
Your
Okay.
standard error is 0.05.
Okay, so what does this number turn out to be?
0.05.
Sigma is 0.05?
Yes.
Is there any more decimals? No, that's it. It's
No.
exactly 0.05. Okay, great. All right. So according to this, anytime I take a sample, flip a coin 100 times, I expect my p hat to be very close to 0.5. If it's more than 0.5, I guess that's okay. But what I'm observing is something out here at 0.62. Okay? So I'm saying, if we assume the coin is fair, what's the probability that it lands heads 62 times or more? Or basically, what's the probability that I would get a p hat of 0.62 or more? Okay, is this okay? So I want to know this. So my z-score is 0.62 minus 0.5 divided by 0.05.
Probability is 0.008.
And I get
Oh,
a
2.4.
z-score of 2.4.
And annotation
And
is
I would get
9918.
1 minus what?
9918.
9918.
There's 0.00282.
10082. Alright, so this is our answer to this. If we assume that the coin is fair, what's the probability that it lands heads 62 times or more? 0.0082. Okay, so less than 1%. 0.82 of 1%. Okay? Not even 1%. So what does that mean?
You have a very small chance.
So it's unlikely for a fair coin to do what we just saw it do. Okay? So I flipped a coin 100 times and it landed heads 62 times. So there's two things that are possible. Okay? It's either we observed something that was pretty rare, that I actually have a coin and this rare occurrence happened where we happen to see 62 coin flips, because that happens less than 1 in 100 times. Or something is funny with the coin and it's landing heads more than it should. Okay? Does that make sense? Right? We could play like we could do a magic trick, right? I could say pick a card, okay? And then and maybe you pick a card, and then I guess it. Let's say I say you picked the 3 of hearts, and I said your card is the 3 of hearts. Okay? Would you be impressed, or would you say, you just had a lucky guess?
Lucky guess.
Probably be impressed, right? Probably. Okay? Maybe not. Okay? But it's true. If I'm just randomly guessing cards, I got a 1 in 52 chance of guessing correctly. Okay? But I think if that were to happen, you guys would be like, oh wow, that was a cool trick, or something. Okay? You wouldn't necessarily believe in magic or anything, but you'd say, oh, that was a cool trick. I wonder how he did it, or something. Okay? Or some of you could be skeptical and you could say, he just got lucky with his guess. Okay? And that's what's going on here. We flipped a coin 100 times and landed heads 62 times. Now, it could be, we just got really lucky and saw a bunch of heads. Or, you know what, this is too rare of an occurrence, so this causes me to believe that the coin is not landing heads with probability of 0.5. Instead, it's landing heads more than 0.5. Right? Is this line of thinking okay?
Yes.
Yes. Okay, good. Because this is how hypothesis testing is going to work. We create a hypothesis, then we gather data, and then we ask, does our data contradict this hypothesis? And the way we do it is we say, well, let's test to see the probability of observing our data if we assumed that the hypothesis was actually true. Okay? So this value here, this 0.0082, this is known as our p-value. Okay? And again, I just want to summarize, try to summarize the ideas going into the p-value. Alright, so a p-value is a probability. Okay, so anytime you see something's a probability, you know that the number has to be between 0 and 1. It cannot be bigger than 1, it cannot be less than 0. The p-value is a probability. It is the probability of observing our data if observing our data, or something more extreme, if we assumed that the null hypothesis is true. So if our p-value is small, what does that indicate?
That it's not likely. It's not exposure.
Yeah, so if our p-value is small, which is what happened over here, that indicates that our data is highly unlikely to be observed if the null hypothesis were true. But the fact that it is our data means it was observed. Okay? If our p-value is small, it means our data is unlikely to be observed if the null hypothesis is true. Can I write H0 instead of null hypothesis? If H0 is true. Okay. But our data was observed. So what does that mean? It means we have evidence to believe that our H0 is false. Does it prove that our null hypothesis is true or false? Does it prove that it's false if our p-value is small?
False.
Yes or no? Okay. So if our p-value is small, okay, again, if our p-value is small, it means our data is unlikely to be observed if the null hypothesis is true. All right. So what happened was we flipped the coin 100 times and it landed heads 62 times. My p-value is 0.0082, which means a coin landing heads 62 times is very unlikely to happen if the null hypothesis is true, or if the coin is actually fair. So coin landing heads 62 times is unlikely to happen if the coin is fair. Yes.
So I know you're saying that the 62 times did happen, and that's why our hypothesis is false. The way the question is posed, it's saying, what is the probability that it lands 62 times? We're assuming it happened, so we do the 62.
It did happen, right?
Oh, okay.
Our coin did land. This is our data. Our data says that the coin landed head 62 times. When we do the calculations, it says if we had a fair coin, that's very unlikely to happen.
So it did happen.
Okay, so it did happen, but our math says that's very unlikely to happen. Okay, so what we have is we have evidence against that initial assumption that a coin is fair. Does that make sense?
Yes.
Good. Okay. But does it prove that my coin is unfair?
No.
No. Okay, so you guys say no. Why doesn't it prove that my coin is unfair? Yeah.
Because it just means it's very unlikely. It could have been a small chance that it happened.
Exactly. Okay? So even though it's very unlikely to happen if I had a fair coin, there is still that glimmer of possibility that it did happen by random chance. Okay? You guys could have been witness to this very rare occurrence of a coin landing heads 62 times just by random chance, right? Okay. It's just like winning the lottery, right? Okay. It's very unlikely to happen, okay? And if somebody has said they picked 6 numbers out of, however many, I don't even know however many numbers appear in the lottery now, but they say, like, I picked these numbers and whatever, okay? It's very unlikely for that to happen, but if it did happen, either two things could be going on. The guy is lying or cheating or doing something, or that person was actually very extremely lucky, okay? Because there's still a possibility that it could happen. All right, so let's try another example, okay? All right, do you guys want me to walk you through another example, or you
Yes.
want to try one now?
No, walk us through.
Walk you through another one. Okay. Huh? You want to try it? Okay. Well, we'll see. We'll see. I guess I'll start off with a few minutes, and we'll see how far you guys get, and then we'll try out. Okay. All right. Let's say it is believed that okay, in a I don't know, you buy packs of seeds, right? In a packet of seeds, does anybody buy seeds and plant them? No. Yeah. Okay. So it's believed that in a packet of seeds, let's say 88% of the seeds will sprout. They call it germination rate, okay? Okay, so basically the germination rate equals 0.88. All right? Or just say P equals see, I'm giving you guys too much information here. Okay. Well, you guys know part of your thing, okay? So it is believed that in a packet of seeds, 88% of the seeds will sprout, okay? You plant a packet of 50 seeds. And only 38 of them sprouted. Wah, wah. Okay. So you are sad. Okay? What happened to my seeds? What went wrong? Okay. So, is it possible that, is this evidence that this 88% is wrong? Or were you just unlucky in your seed sprouts? I don't know. Let's say the packet is a packet of random seeds. Okay, randomly selected seeds. Okay, so is this evidence that the germination rate is less than 88%? get you started. Your null hypothesis, and then you have an alternative hypothesis. Okay, our null hypothesis is that P is equal to 0.88. What is P? What does P represent?
The percentage of seeds that grow.
The
that will
percentage
sprout.
of seeds that grow where?
The standard all
In the population, yes. Of all seeds, okay? Or all seeds of this packet type, okay? So this is the
Mean.
population proportion of seeds that sprout. You planted your seeds and less than 88% sprouted, right? So you are sad and you want to know, does this mean P is actually less than 88%? That they put 88% germination rate on the packet, but there you feel like that's a lie. I was tricked. I thought 88% of my seeds would sprout, but only what, 70 something else. 76% sprouted. Okay, so we want to search for the p-value. How do we find the p-value?
Find the proportion of seeds that sprouted out of the
So
Yeah, okay, so from our data says what? Our data says that p hat is equal to 38 over 50, and that's 0.76, okay? So our data says p hat is 0.76. Does this mean it's less than P? Maybe not. Okay. So how do we get our p-value? Yeah, we're gonna have to figure out a score here, okay? So let's draw a picture. Okay, if the germination rate really is 88%, and I plant seeds, what should go in the middle?
88.
0.88. And what did we observe?
You do 88 or less.
We observed 0.76, and so we want to know we want to know what is this over here. Alright, so my z is going to be 0.76 minus 0.88 divided by the standard deviation, or standard error. Okay, so sigma is what?
You're gonna do 0.84 times.
Okay, what do I do?
0.88
Yeah, 0.88 times
1 minus 0.88
1 minus 0.88 divided by
50.
50. Great. And this comes out to be something.
0.0459.
Thank you.
What would it be, because after the 9 is a 6, so when you round that to 0 and then 6,
Yeah.
I just added another 6 on the end.
Okay. We'll just say 460. That's fine. Alright, 4596, whatever. Okay. So now I have negative 0.12 over 0.0460 or something. Alright, what does this come out to be? Negative 2 point something? Ish. What'd you get? Yeah. You didn't get this far? What do we get? Negative what? 18? No, I don't think that's right. Negative 2.61. That sounds correct. Okay. So now I look at negative 2.61 in the z table, and what happens? What do we get? Point zero zero what? 4.5? Okay. And is that not right?
Yeah, it is.
Negative 2.61?
Yeah, it's 0.0045.
Okay. Alright, I'm trusting you guys, alright?
I trust.
Okay, so my p-value is 0.0045. What does this mean?
It's not very
It's less than 1%.
Okay, it's less than 1/2 of 1/2%. This is a small p-value, and so that tells me what about my seed
Most likely
packet?
not correct. Your hypothesis is most likely false.
Yeah. Okay. So it's possible that I just got really, really, really unlucky with my packet of seeds. That for whatever reason, my random packet of seeds happened to be a dud. That's possible. 1 in 200 packs are that way. Or maybe this claim that 88% of seeds sprout is actually false. Okay? So I'm going to go with that claim is false. So I'm going to say
Well, how would you know?
my p-value, you don't know. You don't know. My p-value is small. So I will conclude that the null hypothesis is false. And the germination rate
Would it be is most likely false, or is our saying it's false?
it's not correct to say most likely. So the germination rate is or we have evidence that the germination rate is less than 0.88. Okay? Yeah, with the way we're setting up our statistics, or our tests, it's not correct to say likely to be false or not, okay? Because the truth is, the hypothesis is either true or it's false, okay? Just like if I flip a coin, before I flip it, I can ask you, what's the probability that it lands on heads? And the answer is 0.5. But once I flipped it and it has landed, it is no longer correct for me to ask what's the probability, because there's no more uncertainty about the coin flip. Okay? With our hypotheses, there's actually no uncertainty about it. The germination rate either is 88% or it's not 88%. Okay? All we have is evidence for or against. All we have is either we have evidence against it or we don't have evidence against it. Okay? And right now we do have evidence against the notion that it's 88%. Yes?
So earlier when you asked, like, does it prove that it's false? Are we basically saying we have evidence against it, but it can't be the deciding factor that it's false?
Yeah, so all of these hypothesis tests, we can't really prove much, okay? All we can say is we have evidence against it, okay? And that's about as far as we can get with proving. We can say we have an overwhelming amount of evidence against such a notion, which might prove things. But in the scheme of things, everything is kind of unknown. Yes.
What would the p-value be if we want to say that we don't have?
Yeah, if we don't have evidence. Yeah, so this is a good question. what should our p-value be for us to say we're not ready to reject the null hypothesis? So here my p-value is like 0.0045, okay? If my p-value is 30%, would you say we can reject or we shouldn't reject the null hypothesis? If the p-value is 30%.
Oh,
We shouldn't, okay? If the p-value is 30%, that means just from random chance, this thing happens 30% of the time, okay? Huh?
So how small does that have to be?
Yeah, so how small does it have to be? The truth is it's up to you, okay? As a researcher, you get the choice of deciding when the p-value is small enough for you to make that rejection or not, okay? Now, there's a caveat there, but so when do we decide that the p-value is small enough to reject the null hypothesis? Okay? Well, we pick an arbitrary value called alpha. Okay? Alpha is called our significance level. Okay? And if p-value is smaller than alpha, we say the p-value is small. And if the p-value is small, that means, what do we do with the null hypothesis? We reject or don't reject? We reject it. Okay, if the p-value is less than alpha, we say it is small, and we reject the null hypothesis. Okay, we say there is evidence against the null hypothesis. On the other hand, if the p-value is bigger than alpha, okay, we say it is not small enough, and we do not reject the null hypothesis. And we say we do not have evidence against the null hypothesis. Is this okay? So, the most commonly chosen value for alpha is 5%. Okay. Okay. 0.05. So if the p-value is less than 0.05, we will say we reject the null hypothesis and that we have evidence against the null. And if the p-value is bigger than 5%, we say we don't. But like I said, you get to choose your alpha. So other common values These are other common values for alpha. But really, you are free to choose any value you want, okay? Almost no one picks, it's very rare to pick an alpha larger than 10%, okay? But pretty much any value between 1 and 10% is generally allowed. And sometimes people pick even smaller values for alpha, smaller than 1%, but generally.
What's the largest you can pick? Sorry?
Rule of thumb, 10%. 10%. You would need an extraordinary reason to pick something bigger than 10%. But it's kind of again, it's up to you if you can justify it. But generally, if you don't see anything listed, assume that alpha is 5%. Okay. All right. So let's try an example. Okay, so let's say a factory says that only 3% of the products have defects. And they produce, let's say, thousands and thousands of these products every day. Okay. They produce say over 100,000 of these products every day. Okay, so let's say you take a random sample of, let's say, 800 products. And let's say you find 28 defective products, or ones with defects, 28 with defects. Okay. So is the factory's claimed rate of 3% incorrect? Or I'll say, is there evidence that the true rate of parts with defects is over 3%? Why don't you guys get started with that, and we'll work through it. Okay, and then after this we'll take a short break, and then we'll finish up. Yes.
Rephrase the question by saying, is the null hypothesis correct or true?
No. Say, you could say, do we have evidence against the null hypothesis? That would be okay. You cannot
Isn't he 28 correct?
So he is 0.03, that's like the population parameter. He hat is 28 divided by his coverage.
Okay.
So that's like our sample.
Do I have
I don't know if it's really he hat, but I don't know like what that is.
Can I clear this or no?
Yeah, so yeah, you're gonna have to go to settings, but like when you do it, you press like a button.
So key equals 0.035, right?
Yeah, yeah, 0.035.
I love how you taught me how to do that standard deviation with the answer. I would.
Isn't it helps a lot better, right?
Because the homework problems are so long. I was like, oh my god.
Assume it's 5%.
Okay, why did you find the standard deviation with this piece?
That's what he's doing. When we have like
Then why'd you find P?
the sample,
Yeah.
because we're trying to see what the probability is of our sample
Alright,
compared to
how are we
the
doing?
regular one.
Good?
Yeah? Okay.
Alright, some of you guys are asking about alpha, so I didn't say anything. Assume alpha is 5%. Okay, let's use.
Whatever what the sample is, but you use the value for like the.
Alright, well.
But that's just what he's been doing, so I just been kind of like.
Okay, I'm just gonna go into.
On the quiz or test, we would state our alpha to back up our.
Yeah.
I pointed samples.
On this quiz, test quiz, I'll probably say either use this alpha or I won't say anything and then just assume alpha is 5%.
It's not 8 and 9, 8 and 9 is next quiz, right? I mean, the quiz on the 11th is on both chapters 8 and 9? Or
Yeah, chapters 8 and, yeah.
Yeah.
Yeah. Okay, let's try this out. Okay, so first off, what is our null hypothesis?
Can I use your
Our null hypothesis is what? It's not 0.03, it's that the null hypothesis is that P is 0.03. Okay? So always make sure, because the null hypothesis is a statement. It's not a number, it's a statement. And our statement is that the defective rate is 3%. Okay? So it is that P is 0.03. Is it P hat? No, it's P, because it's a statement about the population, not about the sample. What is the alternative? Okay. So we're asking, is there evidence that the true rate of parts with defects is over 3%? So the alternative is that our things with defective parts is over 3%. This is what we've got. Is this okay? It's very important that we can set up our hypotheses.
Bless
Okay.
you.
Bless you.
That was so cute.
So,
First with 9 on the standard.
okay, what happened? Now, according to this, anytime I take a random sample, how big was my sample?
800.
My sample is 800 parts, and according to the central limit theorem, it says my p-hat should come from a normal distribution. And what is the mean of this normal distribution going to be?
0.035.
No, the mean is that p-hat comes from a normal distribution, and the mean is 0.03. And my standard deviation is going to be what?
0.0060.
0.03 times 1 minus 0.03 divided by 800. Now, I was walking around and I noticed a lot of people had 0.3. Okay? 0.3 is 30%. That's going to seriously mess up your answer.
The
So-
answer is 0.006.
I have to, this is 0.006.
For P hat, I had 0.035.
Yes, that is correct. Don't worry.
I'm freaking out.
Okay, so yeah, I get 0.006. All right. Okay, so my what happened is that our p hat. Okay, so it says we should be at 0.03, and what do we observe? Our observed p hat is 28 over 800. I observed a defective rate of 0.035. Okay, so I'm not at 0.03, I'm over here at 0.035. And I want to know, what is this area over here? So this is what I observed. According to this,